Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here's your prompt: craft a discourse, an intellectual expedition into the heart of theoretical physics, focused on the 1981 publication Chiral Dynamics and the Quark Model by Gell-Mann, Harald Fritzsch, and Heinrich Leutwyler. This investigation will explore and assess the foundations, arguments, and conclusions presented within this pivotal work, providing a rigorous and insightful analysis suitable for a learned audience. Begin an exploration of chiral dynamics and the Quark model. The year 1981 witnessed the publication of Chiral Dynamics and the Quark Model, a work by Gell-Mann, Harald Fritzsch, and Heinrich Leutwyler that sought to refine understanding of the strong nuclear force and its constituents. This essay undertakes a critical evaluation of the arguments presented within that text, analyzing its core claims, assessing its treatment of chiral symmetry, and examining its implications for the Quark model. The following sections will explore distinct components of the paper, scrutinizing its internal logic and its contribution to the field. Section 1: Introduction and Early Developments. The introductory section of Chiral Dynamics and the Quark model lays the groundwork by establishing the context of quantum thermodynamics, abbreviated QCD, as the fundamental theory of strong interactions. The authors highlight the challenges in applying QCD directly to low-energy phenomena, specifically the interactions of pions, kaons, and other light hadrons. A Q assertion merges chiral symmetry and proximate symmetry of QCD when the masses of the up, down, and strange quarks are neglected, provides a powerful tool for understanding these interactions. This initial claim serves as the central motif around which the rest of the paper unfurls. The validity of this claim rests on the observed approximate masslessness of the pions, which are identified as Goldstone bosons arising from the spontaneous breaking of chiral symmetry. Spontaneous symmetry breaking implies that the vacuum state of the theory, the lowest energy state, does not exhibit the same symmetry as the underlying laws of physics. In this context, the strong interaction vacuum is not invariant under chiral transformations, even though the QCD Lagrangian is close to being chirally symmetric. The authors propose that effective field theories, constructed to respect chiral symmetry, offer a tractable means of approximating QCD at low energies. One may evaluate the strength of their argument by considering the observational support. The masses of the pions, kaons, and the eta meson are significantly lighter than other hadrons, lending credence to the hypothesis that they are indeed pseudo-Goldstone bosons, lighter due to the explicit breaking of chiral symmetry by the small, yet non-zero, quark masses. Quantifying this approximation becomes a primary focus in subsequent sections, through the development of chiral perturbation theory. Section 2: The Linear Sigma Model. The second section delves into the linear sigma model, a specific example of an effective field theory that exhibits chiral symmetry. This model incorporates both scalar fields, the sigma mesons, and pseudoscalar fields, the pions, arranged in chiral multiplets. Gell-Mann, Fritzsch, and Leutwyler present this model as a pedagogical tool, demonstrating how chiral symmetry can be implemented in a concrete frame. The model's Lagrangian, the mathematical expression describing the dynamics of the system, includes terms that are invariant under chiral transformations, along with terms that explicitly break the symmetry. By analyzing the model, the authors derive relationships between the masses of the sigma mesons and pions, and the strength of their interactions. The vacuum, expectation value of the sigma field, a classical value of the field in the vacuum, plays a crucial role in setting the scale of these masses and interactions. A critical evaluation of this section requires acknowledging the limitations of the linear sigma model. At the time of the paper's writing, there was no definitive experimental evidence for the existence of sigma mesons with the properties predicted by the model. More recent experimental efforts have identified sigma meson candidates, but their properties do not perfectly align with the original model predictions. The linear sigma model serves primarily as a theoretical construct, an elegant demonstration of chiral symmetry principles rather than a completely accurate representation of physical reality. The authors acknowledge that the model is a simplified description, emphasizing its utility as a conceptual framework. Section 3 Chiral Perturbation Theory to Leading Order. The third section introduces chiral perturbation theory, frequently shortened to ChiPT, a systematic approach to calculating the interactions of pions and kaons at low energies. The central idea behind ChiPT is to construct an effective Lagrangian, containing all possible terms consistent with chiral symmetry and other relevant symmetries, and to organize these terms in a derivative expansion. Higher-order terms involve more derivatives and are therefore suppressed at low energies. This derivative expansion is based on the power counting theorem, which states the momentum dependence for each term. Gell-Mann, Fritzsch, and Leutwyler focus on the leading order terms in this expansion, which involve only two derivatives. They derive expressions for the pion scattering amplitudes, the probabilities for pions to scatter off each other, and the pion decay constant, the amplitude for a pion to decay into leptons. These expressions depend on a small number of parameters, which can be determined by fitting to experimental data. Assessing this section involves considering the power of effective field theories. ChiPT provides a model-independent framework for calculating low-energy observables, meaning it relies only on symmetry principles and not on specific details of the underlying theory. This makes ChiPT a more robust tool than the linear sigma model, as it does not depend on the existence of particular particles or interactions. The success of ChiPT in describing pion scattering, measured by accurate agreement between theoretical predictions and experimental studies that examine the probability that two pions will scatter off each other, validates its approach. Despite its successes, one must recognize that leading order ChiPT represents only the first step. Corrections from higher order terms can be significant, especially at higher energies. The authors acknowledge the need for calculating higher order corrections and discuss the challenges involved. Section 4 Introduction of External Fields and Axial Currents. The fourth section extends the framework of ChiPT by introducing external fields that couple to the quarks. These external fields can represent electromagnetic fields, weak interaction currents, or even hypothetical forces. Introduction of external fields allows the authors to calculate the electromagnetic form factors of the pions, quantities that describe how the pion interacts with photons, the axial vector form factors, which describe how the pion couples to the weak axial current. A particularly relevant aspect of this section pertains to the axial current. The matrix element of the axial current between the vacuum and a single pion state is related to the pion decay constant. This connection plays a crucial role in the Goldbridger-Treyman relation, a relation between the pion decay constant, the nucleon axial coupling constant nucleon. The significance of this section lies in its ability to connect ChiPT to experimental observables beyond pion scattering. By coupling ChiPT to external fields, the authors demonstrate its versatility and its potential to describe a wide range of low-energy phenomena. The axial current analysis presents a key intersection between theoretical calculations and empirically verifiable predictions. Section 5 Explicit chiral symmetry breaking. The fifth section addresses the explicit breaking of chiral symmetry by the non-zero masses of the up, down, and strange quarks. Gell-Mann, Fritzsch, and Leutwyler incorporate these mass terms into the effective Lagrangian, treating them as small perturbations. This allows to calculate the masses of the pions, kaons, eta meson as functions of the quark. A particularly important result is the Gell-Mann cubomass formula, which relates the masses of the pseudoscalar mesons to the masses of the quarks. This formula provides valuable insight into the flavor structure of the strong interactions and allows for an estimate of the quark-mass ratios. The authors show that the masses of the pions and kaons are consistent with the hypothesis that the up and down quark masses are much smaller than the strange quark mass. Evaluating this section necessitates consideration of the limitations inherent in treating the quark masses as small perturbations. The strange quark mass is not negligible compared to the QCD scale, which governs the strength of the strong interactions. This means that the perturbative expansion in the quark masses may not converge rapidly, limiting the accuracy of the mass formulas. Despite this, the Gell-Mann cubomass formula provides a remarkably accurate description of the pseudoscalar meson masses. Section 6. The quark condensate. The sixth section delves into the concept of the quark condensate, represented by the mathematical notation encompassing the vacuum expectation value of the operator representing the product of the up quark field and its Hermitian conjugate. This quantity is an order parameter for chiral symmetry breaking, a measure of how much the vacuum state deviates from chiral symmetry. A non-zero quark condensate indicates that chiral symmetry is spontaneously broken. Ions are indeed Goldstone bosons. Gell-Mann, Fritzsch, and Leutwyler derive a relation between the quark condensate, the pion decay constant, and the quark masses. This relation, the Gell-Mann-Oakes-Renner relation, provides a quantitative connection between the microscopic parameters of QCD, the quark masses, macroscopic properties of the pions, the pion decay constant, the physical interpretation of the quark condensate is less direct than that of particle masses, or scattering amplitudes. It represents a fundamental property of the QCD vacuum, reflecting the complex interactions between quarks and gluons. Modern lattice QCD calculations, which simulate QCD on a discrete spacetime lattice, provide independent estimates of the quark condensate, which support the values derived from the Gell-Mann-Oakes relation. Section 7. The role of the strange quark. The seventh section examines the role of the strange quark in chiral dynamics. While the authors treat the up and down quark masses as small, the strange quark mass is more substantial. This raises a question of whether the strange quark should be treated as a light quark, amenable to chiral perturbation theory, or as a heavy quark, whose effects can be integrated. Gell-Mann, Fritzsch, and Leutwyler argue that, to a first approximation, the strange quark can be included in the effective field theory alongside the up and down quarks. This leads to a version of chi-pt with 3 light flavors. However, they also acknowledge that the strange quark mass introduces significant corrections, that a more refined treatment may be necessary. The debate over the proper treatment of the strange quark continues to this day. Some calculations in chi-pt treat the strange quark as light, while others treat it as heavy. The choice depends on the specific process being studied and the desired level of accuracy. The inclusion of the strange quark significantly increases the complexity of chiral perturbation theory, demanding a larger number of low-energy constants that need to be determined from experimental data or lattice QCD calculations. Section 8. Higher-order corrections. The 8th section focuses on the calculation of higher-order corrections in chi-pt. The authors emphasize that leading-order chi-pt provides only a first approximation, and that higher-order corrections are necessary to improve the accuracy of the calculations. These higher-order corrections involve loop diagrams, which represent the effects of virtual particles. The calculation of loop diagrams in chi-pt requires regularization and renormalization, techniques to remove infinities that arise in the calculations. The authors discuss different regularization schemes and their impact on the results. They emphasize that the physical observables should be independent of the chosen regularization scheme. Despite the technical challenges, the calculation of higher-order corrections in chi-pt has been remarkably successful. These calculations have significantly improved the agreement between theoretical predictions and experimental data for a wide range of low-energy processes. The success of higher-order chi-pt provides strong support for the validity of QCD as the fundamental theory of strong interactions. Section 9. The eta-prime meson and the axial anomaly. The 9th section addresses the eta-prime meson. This particle presents a puzzle within the context of chiral symmetry, while the pions, kaons, and the eta meson are understood as pseudo-Goldstone bosons associated with the spontaneous breaking of chiral symmetry, the eta prime meson appears to be too heavy to fit this description. The authors explain that the mass of the eta prime meson is related to the axial anomaly, a quantum mechanical effect that breaks the U1 axial symmetry, a symmetry that would otherwise predict a massless Goldstone boson corresponding to the eta prime meson. The axial anomaly arises from the fact that the axial current is not conserved at the quantum level due to the interactions of quarks and gluons. This section reveals the complex interplay between symmetry principles and quantum effects. The axial anomaly, while seemingly a small correction, has a profound impact on the spectrum of hadrons, preventing the existence of a light eta prime meson. The theoretical framework developed in this paper needed to account for subtle, but critical, quantum corrections. Section 10. The role of vector and axial vector resonances. The 10th section considers the role of vector and axial vector resonances, particles with spin 1, in low-energy hadron physics. These resonances, such as the rho meson and the A1 meson, are heavier than the pions and kaons, but they can still influence low-energy processes through their virtual exchange. Gell-Mann, Fritzsch, and Leutwyler discuss how to incorporate these resonances into the effective field theory. One approach is to treat them as explicit degrees of freedom in the Lagrangian, alongside the pions and kaons. This leads to a more complex effective field theory, with a larger number of parameters. An alternative approach is to integrate out the resonances, meaning that their effects are implicitly included in the effective Lagrangian through higher-order derivative terms. The authors argue that, in some cases, integrating out the resonances can simplify the calculations without significantly sacrificing accuracy. The inclusion of vector and axial vector resonances continues to be an active area of research, seeking to reconcile the simplicity of chiral perturbation theory with the complexity of the hadron spectrum. Section 11. Application to weak interactions, non-leptonic decays. The 11th section explores the application of chiral dynamics to weak interactions, specifically to non-leptonic decays of kaons. Non-leptonic decays involve the decay of a kaon into other hadrons, such as pions. These decays are mediated by a weak interaction, but they are also strongly influenced by the strong interaction. Gell-Mann, Fritzsch, and Leutwyler demonstrate how chi-QT can be used to calculate the amplitudes for non-leptonic kaon decays. These calculations involve both the weak interaction Hamiltonian, the mathematical expression describing the weak interaction, a strong interaction Lagrange. The results of these calculations are sensitive to the values of certain low-energy constants, which are not well determined by experimental data. This makes the theoretical predictions for non-leptonic kaon decays somewhat uncertain. Despite these uncertainties, chi-PT provides a valuable framework for understanding the interplay between the weak and strong interactions in these Section 12. Extension to baryons. The 12th section addresses the extension of chiral dynamics to baryons, particles such as the proton and neutron. Baryons are significantly heavier than mesons, and their interactions are more complex. Applying chi-PT to baryons requires new techniques and approximations. The authors discuss different approaches to including baryons in the effective field theory. One approach is to treat the baryons as heavy particles, whose kinetic energy is small compared to their mass. This leads to heavy baryon chiral perturbation theory, an effective theory specifically designed for describing the interactions of heavy baryons. Another approach is to treat the baryons as light particles, on the same footing as the mesons. This leads to relativistic baryon chiral perturbation theory. The two approaches give different results, and the choice between them depends on the specific process being studied. While the application of chiral dynamics to baryons presents greater theoretical challenges, it extends the reach of the framework to more complex and heavier particles. Section 13. Summary and outlook. The final section summarizes the main results of the paper and provides an outlook on future directions for research. The authors emphasize the success of KPT in describing a wide range of low-energy phenomena, from Piompian scattering to non-leptonic kaon decays. They also acknowledge the limitations of KPT, particularly at higher energies and for processes involving baryons. The authors highlight the importance of future research in several areas, including the calculation of higher-order corrections, the incorporation of vector and axial vector resonances, and the extension of KPT to processes involving heavy quarks. They express optimism that these efforts will lead to a deeper understanding of the strong interactions and the structure of hadrons. The closing remarks underscore the enduring significance of chiral dynamics as a tool for exploring fundamental aspects of particle physics. In conclusion, chiral dynamics and the Quark model offered a significant contribution to the field of particle physics through the methodical exploration of chiral symmetry and its application in the context of the Quark model. Gell-Mann, Fritzsch, and Leutwyler provided a framework for understanding the strong force at low energies. While individual claims and approximations require careful evaluation, the overall impact of the work lies in its systematic approach and its enduring legacy as a cornerstone of modern particle physics. The methodologies outlined in this publication continue to inform research and provide critical tools for probing increasingly complex phenomena, solidifying its place as a seminal text for generations of physicists.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.